Thank you for the invitation, and thank you all for being here, hearing me speak some ideas. So I guess this is the more important and general question that I'll try to address. And hopefully, if I do not succeed in addressing this, we can discuss more. And the general story is that, well, making a theory of this question is hard because when you want to model something in machine learning, you have to model the architecture, the learning process, and the data structure. So I will try to make simple choices for each of those points, and hopefully that will represent something more interesting. But to be concrete, let's talk about this beloved generative diffusion, and then let me try to convince you that this is related to memory. So the general idea of generative diffusion is that you have a forward process that it just adds noise on some images from a training set. And then there's a way to invert the stochastic process by removing noise. And if you do this correctly, you can only get back to the original training set. But you can introduce some approximations, early stopping, parameterizations with neural networks that somehow make you go back to new things. So somehow you break memory and you obtain a generative model. And the folklore that, well, I mean, the general idea that I've heard in conferences until now is that, well, there is a deep neural network in it that's parameterizing the process. So it's everything happens thanks to these black boxes. And so in the following, I will show you a simple setting where you have something similar to this, not quite, but something similar, that's no black boxes anywhere. So it's fully understandable what's going on. And I will largely use this concept of associative memory. But I'll try to define it as precisely as I can, because it's more of a buzzwords. So the idea is that let's start with an energy landscape, and the idea is that you construct this energy landscape to have minima in correspondence of things that you want, that are training images, and you will call those memories. And the point is that if you do this and then you run a physical dynamics that just minimizes your energy, eventually you reach your original image, and in the process you denoise the image. And so this is the task of retrieval in associative memory, and you can describe it with something called a retrieval map. That it's this plot. So this shows you how this thing changes with training epochs, but don't look at that. Just look at the red curve for 1,000 epochs. And this is a plot of initial overlap versus final overlap. So the point is you initialize your configuration with a finite overlap with one of your training data points. Then you run your dynamics, and then you measure how close you got to the memory. And the idea is this, that as you can you see the mouse? Probably not. So as you denoise the image, you're traveling up this plot, and let's say that you did not, so you initialize it with some noise. So the initial overlap is lower than 1, and the final overlap is 1, meaning that you effectively retrieved the memory. And of course, if you put too much noise, you cannot retrieve the original memory. And if you start from 1, in that case, you have a fixed point, and then you expect to find overlap 1 at the end.
Why does your 10 epoch curve does not have like when x-axis is 1, why doesn't the y-axis is 1?
When x-axis is no, it's 1. So the red curve. So this is a model that we are training, and this is just to show you that at the beginning of the training there are no memories in the model, because if you initialize it with 1, you go somewhere else, that it's not a memory,
It's not the time of like steps in some kind of Hopfield that's
No, this is a training time. So the colors correspond to the training time to show you that you can build these attractors as you go on. But mostly I want to show you the red curve, and this was the best plot that I had. So in order to go to describe generative diffusion, for example, effectively, we expect to have something like this. So magnetization 1 for the whole x-axis, meaning that even if you initialize with 0 overlap with any of your memory, you go to one of the memories. And this would mean denoising complete random noise, which would mean being a generative model. But this is not the case. And just to show you, okay, this is a picture that would tell you, oh, you start from random noise and then you go somewhere. Everything that will tell is more on this other side of the spectrum. So if you initialize at 0 magnetization, you will not find anything interesting, but this is something that we will try to look in the future. Okay, so this is just to give you some context. I'm keeping in mind generative diffusion as a prototype of the problem I want to describe, but also there is another important prototype of problem that I want to describe, which is mask token prediction. And I would like to convince you that when you are masking a token anywhere in the sequence, either in the middle or if in an autoregressive way, if you want, it's still denoising, because you're used to think of to denoising like this, where you just flip your variables at random. But there's another way of masking, which is just, I think, a special value of the token, which is just mask. But still, it's you can think of it as a version to introduce noise in your image. And so at some point, I would like to connect with this idea of mask token prediction and maybe transformers. So just to rephrase the original question, how do you go from overfitting to generalization? I would say in the context of memory, how do you go from memory to creativity? And the sub-question is it everything thanks to a deep neural network? And so these are the three elements from before. And my choice for doing some analytic calculations would be, let's take a recurrent network. Let's use Hebbian learning as a learning process. And let's use random features examples as a model, as a sensible model for data that's still analytically tractable, but also meaningful. And so before I show you this plot, and what the flavor of the thing that I'm going to tell you is that what happens when you increase the training set size? At some point, the general idea of associative memories is that you reach a storage capacity, after which some extra minima appear in your energy landscape. And these are usually called, spurious states, meaning that they prevent the retrieval task because your dynamics get stuck into one of those. And usually the usual story is that they are bad and they should be removed from the landscape. And instead, I will show you that these spurious minima are the beginning of creativity in these models. So my plan is to first show you that associative memories can become creative, then show you that associative memories can emerge from probabilistic models, so they're more general than they seem. And then I will try to give you a quick sketch on how do I plan to use this for actual modern AI. So let's start from this. And let me try to define a bit better what is an associative memory. And this is inspired by the discussion that I had with Lenka these days. So let's say that it's a self-supervised task model, I'm not sure, but let's say it's a self-supervised recurrent network that can denoise train examples by minimizing energy. But I will actually show you that this is not necessary. We don't need a concept of energy. And I would like to show you that eventually this model can denoise also test examples, not just train examples. Okay, so I would like you to introduce the classic Hopfield network just to set the notation. It's a planted model. I like to think of it as a planted model. So there's an Hamiltonian, and then the assignment for the couplings, which is our learning rule, it's so that you can have some memories, some combinations of binary spins, plus and minus one, as minima of your energy. And obviously there's a threshold. And then you can compute this threshold with statistical mechanics, and in particular as a phase transition, where you have these p order parameters, which are just the magnetizations that are just the scalar product of your configuration with one of the memories. And then you have a control parameter, which is the ratio of the number of memories over the number of variables. And this is called load or capacity alpha. And this is another image of the task that you're doing. And you can think of putting some noise as different ways, like even removing parts of the image. So this was solved in 87 by Amit Gutfreund and Sompoliski, and this is the phase diagram. So you start from high temperature with the paramagnetic phase, where the landscape is uncorrelated with anything that you put into the couplings. And as you lower the temperature, a spin glass phase appears where you have plenty of minima, and your memories are not minima of the landscape. And at some point below the line of Tm, your memories, your data points, become local minimum of the energy. And eventually they become ground states. And this is well understood, except that there's a kind of a secret phase, which is this one, which is the phase where mixtures of states, mixtures of memories become stable. And so this was known even by the original authors, but they never computed the actual transition lines. So we did. And this is the retrieval line for a single memory. So just to refresh, retrieval means that you have memories as fixed points or minima of your model. And the red line corresponds to mixtures of 3 memories and so on, 5, 7. The even ones are unstable for geometrical reasons. But you can go on as much as you want, then the region shrinks. So if you remember this, you will know immediately what comes after. Yes?
Sorry, so below the red line, for example,
Yes.
that all my patterns and all the 3 mixtures,
Yes.
my patterns are all local.
Yes. If you are below one line, that thing is stable. So their phases are one inside each other, but they do not exclude each other. Okay.
Sorry?
Yes?
The combination of 3 patterns is a local minimum, right?
Yes. Yes, the ground states will always be just single memories. Okay, so this is the first ingredient. The second ingredient is random features examples, also called the manifold data. They were studied by a lot of smart people. And the point is, these can also be seen as representing combinations of features. In particular, I will consider binary features that are composed by binary sparse coefficients. And I will call L the number of non-zero coefficients. And I will focus in particular on the case that L is order 1. So this is just to say that each example is a combination of just L features. And the way that they're combined changes with the extraction of these coefficients. So each example is a different combination of the same set. Sorry, the features are just L for each example, but they are extracted from the same set of the same dictionary of features, let's say. And crucially, the lower the size of the dictionary, so the lower D, the more correlated the examples are. Because if the variability of your dictionary is less, then the examples are more similar to each other. What I'm trying to represent with this is that we have some known training images, and the features are just vectors that are shared across these images. So let's redefine the model, which is importantly exactly the same as before. Nothing changes. So still Hebbian learning, but in this case, instead of random plus and minus 1 memories, we have this kind of memories. And the other parameters are the same as before, plus a new set of order parameters, which is just a feature magnetization, which is the overlap against the feature vectors now, not just the examples. And now we have new control parameters, which are just, as before, the load of the model, the dictionary size, alpha D, and then the sparsity of the combinations. So let's run an experiment, which is the same one as I showed you for the retrieval map. We start on top of the thing that you want to probe, let's say a training example, x0. We run a dynamic until we reach a fixed point, and then we compute the overlap, which we call magnetization. So if magnetization is 1, then the thing that we are probing is a fixed point. And this is the result of the experiment. So as a function of the load, we have magnetization, and then we have a very common storage phase where we have a maximum number of vectors that we can store. And if you note, then the critical capacity is around 10 to the minus 2, which is 10 times less than just Hopfield networks on uncorrelated data. So this was known, like storing correlated data is harder than storing random data for Hebbian learning. But if you keep increasing the load, something weird happens, which is the magnetization comes back up, which is weird because the model is saying, okay, at some point you gave me too many memories, I do not remember them anymore. But if you keep increasing of 2 decades of alpha, at some point the associative memory says, oh yes, now I recognize what's going on, which should not be like this, should be something else. And in fact, now that you have correlated examples, you can also have a test set. And you can probe the magnetization of the test set examples. And in fact, these are 2 different phases, because at low alpha, that's just a storage phase. But at high alpha, this is what I call a generalization or creativity phase, because the network has a memory of things that it never saw before, which looks weird. But we have an explanation for this in the next slides. And it relies on a third transition that I will call the feature learning transition, which is where feature vectors becomes themselves a fixed point or local minima of the model. And so this is the phase diagram. As a function of, on the x-axis, we have alpha D, and the lower alpha D, the more correlated the examples. And on the y-axis, we have alpha. And so let's start from here. Data are almost uncorrelated. So we recover the critical capacity of Hopfield networks, which is around 0.14. As we keep decreasing alpha D, the data become more correlated, so the critical capacity becomes lower. And at some point, data becomes so correlated that a new phase appears at high alpha in the blue region, where features become at least local minimum. So this is the situation. This is just a normal storage phase, and this is the feature learning phase. And everything is much easier if you realize that when P goes to, so when alpha goes to infinity, your Hebbian learning just converges to a new Hebbian learning matrix with the feature in place of the memories. And so if you understand this and you remember the mixtures from before, the black magic is explained. Do you have questions on this? Yes?
Like you seem to have a vertical asymptote at which the blue region exists.
Yes.
So the intuition holds only for alpha D that is small enough.
Yes, exactly. In fact, because of this analogy that when you go to alpha infinity, you converge to an Hopfield model in the features, that vertical limit is the same capacity as Hopfield, but for the features. So alpha D 0.14. But thanks for the question, because I forgot to say that. Yes.
You know, the feature phase is not the pattern phase, or is it still?
Sorry?
In the feature memorization phase, do you still remember the individual pattern?
No.
No. Different than the previous.
Yes. Yes. Unless you go in another region, which is called the creativity phase, which is this. So let's remember this. And this is the phase diagram of the problem. So on the vertical panel, we have the phase diagram of a standard Hopfield model, but with the features in place of the memories. And if you remember the plot that I showed before, then you also remember that there are these mixtures phases. And in fact, this is and then you can project this at finite alpha, but nothing changes. Just they just shrink. And so this is a single feature retrieval phase. And actually here, at some point, the features become ground states, and they will always be ground states. But then you have this 3-feature mixture retrieval and so on. And then you can remember, you can realize that mixtures of features are precisely the way that we generated the patterns themselves. And so the model can exploit these spurious states, not all of them, because we also have bad spin glass states, but the model can exploit these mixtures of features to represent things that it never saw before, too. So in the red line, here, yes, you also remember training sets. Also, it depends on L. So if you generated your data points with a higher ratio of with more features, then you have to go to smaller phases.
Remind me, E, N, and D again. D is the dimension.
D is the dictionary.
Yeah.
N is the number of neurons. So that is the visible dimension.
P is features.
P is the number of data points. So alpha is the load, as always.
Is our little n.
Yeah.
N is our little d.
Yeah.
And d is our little p.
Oh, well, that's clear.
Okay, sorry, but also I am using the notation from the 90s, so it's your fault that you changed notation.
Just wanted to be understood by the rest of
Yeah, no, you're right. In fact, this is why some Polinsky love this, because I was using this notation.
Sarah is calling this Sompolinsky imperialism.
Yeah, exactly. I am a victim of this. But in the just to finish this picture, the 7 mixture is we have a landscape like this. Ground states are single features, and then as you increase the order of the superposition, you go higher in free energy. And this is it. So we plot this line for the transition to 3 mixtures here, and it matches the.
How do you interpret? So for creativity, you need a small alpha D.
Yes, or large alpha. Yes.
Yeah. Also, how do you interpret that? That alpha D needs to be small.
So the bigger alpha D, the bigger the dictionary.
Okay.
So it's harder to infer it. It's basically the rank of the matrix factorization. It's the ratio of the rank. But here you also have this L, which complicates things. So maybe this is why this is simpler than just generic matrix factorization, because you have this role of the sparsity of the combinations too. Okay, and I want to call this creativity. Oh, and I did not used to call this creativity phase transition, but then Sune Ganguly suggested I would call it creativity. So I'm going with it.
Imperialism.
Yeah, so many imperables.
If you don't put this constraint on L, do things change or not?
So L does not matter in training. So the blue line is completely independent on L. And this is a big mystery. I have no idea why.
The red and orange?
Yes, they do depend strongly on L. So if you go to higher L, you need higher alpha to find it.
So you're saying the blue line, so the transition at which I start storing features.
Yes, it's independent on the distribution of the superpositions in the training set. Let's say independent. It weakly depends. Like you would not be able to see the difference in this plot. So, okay, this suggests a new perspective on generalization, which is look for attractors near test examples. But I showed you a very simple model with a very simple data set, maybe with also binary variables. So maybe everything, I had the doubt that everything was an artifact of spins. So how specific is this? Can we do better? Can we do something more general? And this is why I will tell you now about a slightly different story, but in the same spirit as what I said before. And this is, let's start with a probabilistic model, and then I will show you that we are actually building a better associative memory, so a more powerful Hopfield network. So there's this thing called pseudo likelihood, which some people would like to call conditional likelihood, but it's just a very slight modification. It's an approximation in the setting of maximum likelihood. So you just have some variables and some likelihood function, and some data set, and then you want to infer the couplings J that parameterize the likelihood that maximize the likelihood of the data. And so you write a negative log likelihood loss like this. And so you evaluate the log probability of each data point, and then you construct a loss, and then you minimize it. But depending on the choice that you make for the likelihood, you may have to evaluate a partition function, which is difficult. And so in some cases, you do this pseudo likelihood terrible approximation, which is just, let's approximate the joint probability with the product of conditionals, which is only true on a tree, for example, or in specific cases like autoregressive models. But regardless, I will do the easiest thing. So I know this is wrong. I'll just do it regardless. And you obtain a new loss function that we will call negative log pseudo likelihood, but doesn't matter. And the nice thing is that if you consider the simplest physical model for this kind of likelihood, which is just a two-body model, then well, maybe you don't even need that hypothesis. The point is the loss function factorizes. So you have n independent problems, one for each thing that you want to predict. And so you can train your model in parallel, one for each missing token in a sense. Okay, so let me give you an intuitive reason why this is an associative memory. So you have this loss function, but you can write it also as you have an energy term, in this case, the sum over I of the log of P, as some energy, E, of all your variables. And then you're evaluating this thing on your data points. And then you are minimizing the sum. And so one way you can think about this is that you have an energy, and you're asking that the sum of these energy evaluated on your data points is minimum. And one way to solve this is by creating an associative memory. So you just decrease the energy of your data points, and that's it. And then you create these valleys that should converge to the data points. And to show you this, I will consider this dynamics, which is just, since we're using conditional probabilities, it's natural to use conditional probabilities also to run a recurrent network. So at each time step, we just update all the spins with their conditional probabilities. But actually, I will do something even stupider, which is zero temperature. So at each time step, I just consider the argmax of the probability, which is just to say, I am at zero temperature, and I flip the spins with the sign of the local field. So the most basic thing that you can think of. Okay, and so the thesis is that the pseudo-likelihood action produces an associative memory. And here I'll show you the basis of attraction size. So if you remember the retrieval map, the width of the plateau in the magnetization can be thought of as the basin of attraction, and we measure that size. And here I'm showing you the basin size as a function of alpha, both for asymmetric couplings and symmetric couplings. This difference is important because since the problem becomes factorized on each side, the couplings in general are asymmetric. So you lose the concept of energy here, which is important for two reasons: neuroscience, but also that asymmetric couplings work better. So there's also a computer science reason why we don't care about putting an additional constraint on our scheme, because it just reduces the capacity as you see here. So this is just an experiment to convince you that we checked numerically that this is indeed a memory. And then there is also a theoretical reason why. So this is the negative log pseudo likelihood loss, which is just basically it's the numerator of the exponential, the Boltzmann distribution, and the normalization of the conditional probability. And you can rewrite this as, so this is factorized with respect to I, so we can take a single addendum and rewrite it as a logistic loss. So this whole story from probabilistic models is just saying we are training n perceptrons with a logistic loss. And this is also related to mask token prediction, because you're removing the spin I from each of those perceptrons. So when you're trying to predict a token, you're removing its channel from the output, from the input. So once you realize that this is a logistic loss, then you remember a result that says, okay, norm diverges if you do not regularize this object. But while the norm diverges, there's an implicit bias where, so it was found by Sudri et al. In 2018. So while the norm diverges, the rest of the model is invariant with respect to changes in the norm. And so the direction converges to the solution of this problem, which is solving perceptions with margins. So implicitly, when you train cross entropy, you're maximizing the margins, the classification margins of your perceptions. And what happens when you maximize classification margins? You create bases of attraction. So this is the plot, again, a retrieval map, just like the one that I showed you before. So initial overlap on X and final overlap on Y. But I'm comparing perceptions trained without margins. So this is the blue, the pale line is 0 classification margin. And then I keep increasing the classification margin. And in fact, I show you that these bases of attraction appear. But I'm also showing you the red line, which is the same as the first plot, which is the same thing trained with pseudo likelihood, which does better than the perception rule with maximum margin. They should be equal. We think they should be equal, but the point is the perception rule is very hard to train and to converge. So maybe we need an exponentially many steps to converge.
Other lines, what is K?
K is the margin of the perception.
What is the
So this plot should support the fact that pseudo likelihood is maximizing the margins, and it's a simulation. But we also have, again, now I'll go back to the theoretical framework. So the story is the following. Pseudo likelihood is the logistic loss, and logistic loss has an implicit bias towards maximum margin solutions. And this is a result by Sudri. And then a result by Gardner in the original paper. Large margins imply large bases of attraction. And then we have a third part of the story, which is my favorite, that Hopfield learning appears as an early training limit of pseudo likelihood, or this logistic loss, in this way. So this dashed line, let's say, the green line is the training in is a training of a logistic loss in this setting, and it resembles an interpolation between Hopfield learning, which is this green dashed line, maximum stability, which is maximum margins, and then bias optimal. And then this plot is mysterious, I understand. And in fact, it will also show some new neural scaling laws, but maybe if we have time, we can talk about that later. What I'm just saying is, since we realize that this process is interpolating between Hopfield learning, which is an associative memory, and maximum stability, which is also an associative memory, the whole thing is an associative memory along the whole training, basically. So this is just to give you the theoretical context. Yes?
So the margin, you fix it from the model, or is something that you put as a parameter?
That's a great question, because it's implicit. So at a given capacity, alpha, the model spontaneously finds its own margin, the best one possible. So the model converges automatically to the maximum margin available at that load, which is convenient because you do not have to fix it a priori. Because you do not know a priori what margin is compatible with your alpha. Okay. So this is the experimental phase diagram of the same thing that I showed you for Hopfield networks. So on x-axis, I have alpha d, and on y-axis, I have alpha. And let's focus on the leftmost. Yes?
Just the data is the same as before, notably F are binary and C are binary,
Yes.
0 and sparse.
Yes.
And the value of L is important?
Is 3. Yes. It's important because, well, qualitatively, no. Quantitatively, yes. So L here is still 3. because it's the easiest problem that we can do.
Okay, and if it was large, then
You need higher alpha.
which one? The alpha or alpha D?
So this is for L3. For L5, you need to go higher in alpha. So this thing goes below, I think. Well, let's say this one, like the feature learning transition becomes much higher. No, I said this is, it's the generalization thing. This is independent on L. So let's say that this generalization thing goes higher in alpha and lower in alpha D. So it shrinks vertically. Okay, so just to repeat what this is. So the color is just the magnetization. So yellow means 1, and blue means 0, and green is 0.5. But the point is, we also plot the red curve, which was Hebbian learning from before. And this was the storage phase from Hebbian learning. And this is just to show you that the storage capacity is increasing greatly, but not just that. So from information theory, it should be easier to store something that's more correlated, right? Like completely random patterns are harder to remember. So it doesn't make sense that the capacity decreases with the correlation. And in fact, now that we have a better learning rule, which is this pseudo-likely thing, the storage capacity increases by increasing the correlation of the data. This is the first thing to notice. The second thing to notice is that this region here, so the region where this correlation matters, is the region where you store the features. So once again, you have this recurring thing, and then you ask, is this a fixed point? Yes, features are fixed points in this yellow region, which is 3 times as big as before. And then you have this sliver, which becomes zoomed here, which is the generalization phase, which is probably the thing that becomes the largest. So you see that the increase between this sliver of the Hebbian learning thing. This is just to say, the story is the same as before with Hopfield networks, just better and more robust, and everything makes a bit more sense, I think, now. Also because this thing also works on real data without any change. So now instead of having plus and minus 1 from random features, we take a binarized version of MNIST. And so we get this picture. I will show you the pictures of MNIST in a moment, but bear with me. This is similar to the plot, the memory to creativity plot that I showed you for Hopfield networks. You just have the magnetization or overlap on the y-axis and the load on the x-axis. So at low load, you find that the magnetization of the training examples is 1, and both test and random examples are low, which means that here you are memorizing training examples and nothing else. And as you keep increasing the load, at some point you exit the storage phase, but instead of going to 0 here, you already go to 0.85. And the reason why I believe that this is a generalization phase is because training and test magnetizations are the same. And we're also checking that random examples are still not magnetized, because that would mean that everything is stable.
They're a bit. But they're a bit magnetized.
A bit, yes, because we have a reason for that, but it's still open.
But how is it possible? Because for the random ones, you're just predicting random numbers. So how could you manage to predict it? Or that's not what you're holding.
So
Maybe.
okay, this should be interpreted as, so I initialize with magnetization 1, and I arrived at magnetization 0.4. So I lose 60% of the spins from my initial configurations.
So for all 3 curves, the initial magnetization is 1.
Yes, for every curve, the initial magnetization is 1. So you're asking, if I start there, where do I go? And if it's 1, you stay there. And if it's not, that's the distance that you travel. So the question is 0.85 good enough?
It's not really how good you are at predicting something that you do randomly. It's whether you stay close to initialization.
Yes.
So it could be that you stay at initialization, but you didn't learn anything.
Yes. But now I'm going to show you What if you initialize with something that you never saw before? What if you stay there? So what if you recognize something new? And you do something less obvious, which is this. So this is training examples. So I'm taking now the rightmost plot, the rightmost point. So this is probably 40,000 training images, something like that. So on the first column, you find the inputs, and on the right column, you find the outputs for training examples. And this is for test examples, which is, there's no other way to assess this other than by eye, I would say. But by eye, you see that this is a difference in magnetization of 0.15. So if you had, these are different images. If you had magnetization 1, it would be the same image. But this is slightly different, but I would say in a good way. So it's not that you're mapping your 4 to something completely different. You're mapping your 4 to a slightly modified 4. And so I would say that in this specific case that we can assess by eye, the test magnetization of 0.85 is decent. And this is what I mean when I say that this also works for real data, because if you try to do the same exercise with Hopfield networks, nothing works. You get a ferromagnetic minimum in the center that's just everything black and nothing interesting.
Just a question, why do you validate it this way, with this kind of magnetization between your fixed point and initialization? Because you also said you defined associative memory by being a denoiser.
Mm-hmm.
If you actually validated it on denoising, then you wouldn't have this annoying property, right? Random data, you just can't denoise, like zero. Right? Whereas the structured data, you are able to denoise. So wouldn't that be a more proper kind of way of validating it?
Yes, but the story is already complicated as is, so we left denoising for the appendix. But yes, we did similar things for denoisings.
It's in a sense more complicated because here, right, I'm really confused by this curve where for random data you actually do have magnetization, and it's just something that is because you're looking at the correlation with the initialization, not with the correlation with the structure. Whereas if you were validating on denoising, you would just be completely decoupling the two.
But we initialize the non. In each case of the two, you compare to the non-noisy version. So the difference is, if I go back to, so the difference is either we initialize magnetization 1 or lower than 1, right? So what I showed in the other plot is the final overlap. But the final overlap can be computed either for magnetization 1 or for magnetization 0.8.
Right, but for denoising, okay, I mean, of course, like the noisy, even noisy random vector is correlated with your original random vector, unless the noise is infinity, right? But this you subtract because you can, like, you can denoise something noisy. You know, the measure should be, are you better correlated with your clean vector than the noisy vector? And if you are, then this means you learned something. Right?
Yes.
And if you do this on a random vector, then there is no way you do better than 0 or better than square root of n.
Yeah, so you're right.
That would be like a more proper.
This could be a yes. You're right.
It's the same experiments. You just, instead of plotting the magnetization between the initial and final, which seems a bit mixing several effects here to me. Whereas the denoising is really kind of, statistically proper way of.
Yeah, no, I think about it. I think you're right. But let's say that here I'm not, even though I'm talking about denoising, what I'm doing here is just memorization, like fixed points.
Change the story.
No, I agree.
I think it will make the picture like cleaner, right? This green curve would be a 0.
What I'm just saying is denoising depends also on the size of this basis of attraction. Because you can put a certain amount of noise and then check if you can denoise that amount. And so that depends on whether this basin is large enough. While by checking only this point, it's just we have one variable less, and so. But for a follow-up, I think it would be a great thing to measure. So basically, my story is over. So I showed you MNIST, but this pseudo-likelihood thing comes from modelization of protein sequences, which use Potts variables, but except for that, it's exactly the same story. So you're trying to model some probability distribution over protein sequences, and instead you do this approximation of conditionals, but everything is defined on Potts variables, but everything works exactly the same way. So you have a storage phase at low alpha and a generalization phase at high alpha. The difference here is that it's much harder to assess the quality of generalization. Because yes, these two lines collide, but this jump now is larger. And we didn't have time to go into the details of the biology, but I suspect that a model can generalize, but it can generalize poorly according to this scheme. Because you would like this to be 1, so that when you present a new sequence, the model says, yes, I recognize this. When that is not 1, we don't know what to do. And so I am entering now I'm entering the realm of not well-defined things. And so if you have any suggestion, it's really...
Sure, sorry, I probably just was not paying attention. What was not well-defined? So I understand these are some proteins.
Like before.
Proteins.
So here,
20 amino acids, and then?
What I'm saying is this gap here,
yeah,
we say it's good because then we can plot the things and by eye say that this difference is decent.
Okay.
In protein sequences, we do not have such an easy comparison. That's the only thing I said.
And the gap in that case?
The gap is large now. It's not just 0.15, it's whatever it is, 0.4. Okay, so just a recap for these two pieces of story. Hopfield networks can store hidden features and can store previously unseen examples. And more general, associative memories can work without symmetry, actually even better, and can emerge from probabilistic models. And this is a list of people that I worked with. So the first papers on Hopfield networks I did with some people with Bocconi plus Silvio Calai, which is a master student of mine in Rome, and now is doing PhD. And then this whole thing on pseudo-likelihood I did with mostly people in Sapienza, and in particular PhD students. So just an advertisement to our PhD students. These are the main references to the things that I showed. And then if you have a bit more patience, I would tell you some flavors on how these things can be ported to AI. So once more, this is my definition of associative memory. So I hope I convinced you that you don't need energy because you just need this conditional probability thing. And this is a work that we did on diffusion models with Dmitry Krotov and Luca Ambrosioni, let's say. And we showed that this idea of spurious states can be found also in generative diffusion. So here we show in the memorization phase, so few data points of a generative model, that you have a training set and then you generate some data with a synthetic set. And in memorization, you can find the same thing multiple times because you memorized it. While in the generalized phase, so a lot of data points, when you generate a sample, this blue, and then you compare it to the other generated ones, the closest that you find in the synthetic set is different, while it's also different from the closest in the training set. So you say this is a generalized phase because you generate new samples and you cannot generate twice the same one. But as the training data increase, we show that there's an intermediate phase at the very edge between the two, where you can generate a new picture, but you can also replicate it, which is more similar to this idea of associative memories that memorize new things. So because replicating the same thing at training time is similar to an idea of memory, but just a memory of a new thing. And I just want to compare this to this story that as you increase data points, you create spurious states, but these spurious states can be benign in a sense. So this is an ongoing project. I think the paper is out since a long time, but this is an ongoing project. We are not sure if we have something more yet. And finally, maybe what I'm saying is simple, is that one of the tasks that you can train a transformer to do is simply mask token prediction. And I hope I convinced you, especially with this pseudo-likelihood story, that the way that you model predicting a missing token, it's basically a conditional probability that give me the yellow token given the others. And hopefully you can write an equivalent physics model where instead of binary spins, you have some high dimensional vectors, maybe vector spins. In fact, we also published a paper on vector Hopfield networks in the meantime. And you can write this mask token prediction process as a sort of a denoising process, where at each time step you update your prediction of your tokens. Here I wrote that you decrease the energy at each level, but what I'm thinking really is you move depending on the pseudo likelihood, not the energy. So there's no general differentiable function that gives you a gradient. So if you, going back to the original question, this is more of a wishful thinking for an ERC level project. How to go from overfitting to generalization in transformers architectures. And the stupidest thing that you can try is, I never understood this image, so let me replace this image with something I understand, which is, okay, input, embedder, self-attention 1, multi-layer 1, and repeat. And maybe if you do this other exercise, which is just input, embedder, self-attention layer, but instead of having different layers, you repeat the same layer a lot of times, maybe this converges to a fixed point, and then you can use this for the embedder. This is just an exercise. We tried it with mixed results, but this was before that we tried the whole pseudo-likelihood theory, so maybe there's something to do in this direction. And so just a recap for future directions.
What you showed us is doing the opposite. If you go slide back, you got rid of the self-attention and you only used perceptron in your
yes, but the multi-layer perceptions in self-attention,
single layer one, and then you made it recurrent.
Yes, but they do not mix different tokens, I guess.
I mean, at the moment you trained it on the proteins. That's a bit like having to.
Oh yeah, sure, I agree. Yes, well, maybe we do linear self-attention would be enough. I agree.
But maybe not, because that would overlap to a whole. Oh, I mean, I don't.
Well, the pots, the protein thing was basically pots variables with linear tension in this scheme. But I mean, this is just a flavor. Maybe we can, I can think about this a bit better. So the thing that I care most about is this idea that there's a creativity phase transition in associative memories. We can use this to describe generalization, possibly in diffusion models, possibly in transformers. Maybe Boltzmann machine is an easier setting. And I believe that we also need a better models of data, because yes, random features seem to work as a decent approximation, but also the spectrum of principal components for random features is bad compared to those of real data sets. So maybe we need the better models of data. I'm thinking to the work of Matteo Negri, for example. And also we have some consequences for the theory of deep networks, where this idea of logistic regression has some consequences for neural scaling laws. I'll just flash some images because I already spoke a lot. But the idea is that if you solve the curves for different values of alpha, then you realize that you have some scalings for the early training regime and then for the optimal early stopping points. And these scales as power laws of the load, different power laws in each case. And then all the curves can collapse if you divide them between with certain parameters. So there seem to be that this pseudo-likelihood story seemed to be related to some scaling properties in perceptrons that also translate to real deep architectures. And we don't know why, but the regularities seem real. And so we will continue to work on this. If you have questions, I'm happy to talk. Also, again, I'll be here until Friday. So if you want to chat about anything that I said, especially the stupid things, I'll be happy, and thank you.